Good afternoon, everyone. This next section is called Related Rates, section 3.9. Before you start the section, though, make sure you download the appropriate worksheet for the section because it's all word problems, okay? And you can find it on Canvas. There should be a link next to this lecture that says, worksheet for 3.9 downloaded. Or you can go to the Files tab on Canvas under our course, and you'll see the sheet right there. It's a PDF. The name of the PDF is called 3.9 Related Rates Worksheet. All right. So what are related rates? As I said, they're word problems. They're basically asking some question, how fast something is growing or shrinking. And when I say how fast something is, like, what is that something? It's just different shapes. It could be like balloons, volume spheres, stuff like that. Okay. So if we look at the first one, let me pull it up. The first word problem says, okay, a pebble is dropped into a calm pool of water, causing ripples in the form of concentric circles. The radius r of the outer ripple is increasing at a constant rate of 3 inches per second. When the radius is 4 inches, at what rate is the total area of the disturbed water changing? So basically, if we draw a picture, right, probably everyone's thrown a rock into the water, right? Like when you throw a rock into the water, what does it do? It makes little circles that expand slowly outward, right? They're basically going out, and the circles or the ripples get bigger and bigger and bigger. So we have some kind of circle, right? It's constantly growing. And they're asking, when the radius is 4 inches, at what rate is the total area A of the disturbed water changing? So how do we approach these related rate problems? Well, the first thing that you want to do is figure out what is the shape or thing that they're talking about. Are they talking about circles, rectangles, triangles, something? It's correlated to some kind of shape, okay? Then once we know that, let's write that formula down. Okay, so this is a circle, right? This is a circle that's just consistently growing. So we're probably going to go with area equals pi r squared. So just write down that base formula that you're going to be working with. Now what we want to do is we want to label what we know and don't know, or what we're being asked. So they said, first sentence just says, the rocks drop into the pool or water. And it says the radius r of the outer ripple is increasing at a constant rate of 3 inches per second. So the radius of the ripple, meaning how fast these ripples are growing out, it says it's 3 inches per second. Now, what is that right there? So the key to working out these problems is just making a list of what you know and what you're being asked to find out. So we can make like a we know column, okay? We know. Because we're always going to be given certain parameters. What do we know? We know the radius of this outer ripple is increasing at a constant rate of 3 inches per second. What is that though? Is that r? No, that's radius, right? It says the radius is increasing at a constant rate. So this is not r equals 3 inches per second. This is dr dt equals 3 inches per second. Now, where am I getting all this from, right? Because it just seems like I'm pulling it out of thin air. Well, I'm really not. So that 3 inches per second, that's a rate of change. Rate of change, remember, is what? It is a derivative right here. So this dr dt, this is basically the radius changing with respect to some amount of time. As a matter of fact, all your related rate problems are always going to have d dt. So instead of, how when we first looked at derivatives, we were doing ddx of everything. With these, you're going to have ddt because it's always with respect to time that things are shrinking, expanding, whatever. So we know that dr dt in this instance is 3 inches per second. Now, the next sentence, they say when the radius is 4 inches, at what rate is the total area of the disturbed water changing? So what does that mean? At what rate is the total area of the disturbed water changing? Well, they didn't give us that, right? That's what we're looking for. But they're saying when the radius is equal to 4, right? 4 inches. at what rate is the total area of the disturbed water changing? So whenever you see that phrase changing, something changing associated with some kind of letter, then they're talking about that letter's derivative. So when r equals 4 inches, the radius equals 4 inches, how fast is the area of these circles increasing? So we want to know dA dt is equal to what? So that's what we're looking for. Again, they're saying at what rate is the total area? When you see that phrase, at what rate, that signifies they're talking about some kind of derivative of something, of some letter within the formula. So they gave us a couple things. They said the radius is growing at 3 inches per second. That's our dRdt. And they're being very specific. They're saying when the radius of the circle hits exactly 4 inches, how fast is the area expanding? How are we going to do that? Well, that's where it comes back to this formula right here, our base formula. I say base before we derive it or do anything to it. So what are we going to do? We are going to take ddt of both sides. You're always going to take the derivative with respect to time when you're doing these related rate problems. So ddt of A equals ddt of pi r squared. So we're taking both. Remember, there's only two variables right here. There's A and R. Pi is not a variable. That's a constant, right? That's like, 3.14, blah, 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 like that. So how do we derive this? This is where implicit differentiation comes from. Kind of like when we did ddx. Remember, if we had ddx of y, what was that? That was just dy dx. Same concept here, except now it's just you're using t in the denominator and you have different variables besides y. It's still the same thing though, okay? So if I take the derivative of area with respect to time, it's just dA dt. That's it. Equals. Now if we do the right-hand side, remember pi is a constant, okay? If this was like 5r squared, you just pull the 5 out in the front. So we'll do the same thing with the pi. What's the derivative of r squared with respect to time? Well, you have to do the power rule right here. Kind of like if we had ddx of y squared, what would that be? 2y and then dy dx. Same thing right here. If you take the derivative of r squared with respect to time, well, you got to do the power rule first. So it's 2r to the first, and then times, we have to chain the r with respect to time. That's dr dt. Okay. So do we have enough information to figure out how fast the area of the pebble, or I'm sorry, how fast the area of the circle or the outer ripple is increasing when the radius is equal to 4 inches? We sure do, because look at what we know. We know r equals 4. We know dr dt equals 3. What are we looking for? dA dt, right? That's the question mark. Remember, pi is not a variable. That's an irrational number, right? Again, it's 3.14, blah, blah, blah. When you're working these problems out, leave the pi in its exact form. Do not convert it to 3.14. If you notice on the homeworks, or the answers, everything, they leave the pi there. So do not multiply the pi through. Don't look at that. So let's substitute what we know. So we have dA dt equals 2 pi, and then r was 4 inches, and then dr dt was 3 inches per second. Now I'm putting the units. Are they important? Absolutely, right? We're talking about shapes of things growing or whatever, so it is important to keep the units. On WebAssign, it has the units already in the answer box, so don't type 5 inches and then you're submitting it and it's wrong, and then you email me and you say, hey, why am I getting it wrong? And I'm gonna say, well, because there's already inches in the answer box, so the computer thinks you're going 5 inches times inches or 5 inches squared. So again, don't type the units in for the WebAssign. But future problems or your engineering courses, of course the units are all going to make a difference. You're going to have to supply them. How do we supply them? You just multiply and divide them out, right? So dA dt, or how fast the area is changing at this specific instant when the radius equals 4 inches, is 8 pi and then inches squared per second. So 8 pi, where's that coming from? Just 2 pi times 4 is 8 pi. Where's the inches squared coming from? What's inches times inches? Inches squared. The bottom is just seconds, right? Like you could say over 1 if you want. So we just bring the seconds along. This would be your final answer right here. Again, no decimals. No decimals at all. Leave it in exact form unless the directions ask for it. I think there is one problem on this homework where it asks for decimals, but it will be very specific. It will say round your answer to the hundredths place or 2 decimal places or whatever. If it does not say anything about rounding, don't you dare put pi into the calculator as 3.14 and crank out the answer. No, you leave it like this. So just to recap how to solve these related rates, what you want to do is first identify what kind of shape are you dealing with, right? Because we need some kind of formula to work off of. In this case, we had a circle. Sometimes it could be a sphere, a cone, a triangle, a square, some kind of shape, okay? You should be able to get the formula for it. And then from there, you want to make a list of what you know, right? Because usually the problem will specify some part of it, okay? And when you see that phrase, a rate, constant rate, or just rate, that tells you that the number that follows it is some kind of derivative, okay? How fast that certain variable is changing. Again, like in our problem, it said the outer ripple is increasing at a constant rate of 3 inches per second. That means that signifies your dr dt, all right? And then everything else, if they do give it to you, they'll label it in its respective form. Like for the last sentence, it says when the radius is 4 inches. In that case right here, you know r equals 4. And again, when they ask at what rate is the total area A of the disturbed water changing, when you see that phrase at what rate, that signifies d of whatever variable over dt, like that. Once you figure out what you're being asked for, go back to your base equation, right, of the shape that you're dealing with, and you take its derivative with respect to time. You will always have to do the chain rule, and implicit differentiation will come out of it because we're always deriving with respect to time. We don't have any t's in these formulas right here. So you're always going to have d something over dt popping out. Like in this case, we had a dA dt and a dr dt that popped out. Remember, it works the same way like when y'all did ddx of y, the derivative of that was dy dx, right? Or if you had ddx of y cubed, it was 3y squared dy dx because you're doing the chain rule. And then once you work it out, watch the units, right? I know WebAssign has the units, but when y'all take future engineering classes and stuff like that, you will have to supply the units. Again, you're just multiplying inch times inches squared or squared inches. And then the seconds on the bottom, you just bring it along. So that is the first problem. If we go on to the second one, number 2. Again, make sure y'all get this sheet, right? You can download it from Canvas. The link should be associated or right next to this video is a downloadable link, or it is on the Files tab. Just look for 3.9 related rates. It's a PDF file that you can download. Now, number 2 is talking about a square, right? It says each side of a square is increasing at a rate of 4 centimeters per second. So the square, it's expanding, right? Just getting bigger and bigger, and it's increasing at a rate of 4 centimeters per second. Then it's asking us, at what rate is the area of the square increasing when the area of the square is 9 square centimeters? So remember, to start these out, what do? You want to find what's that base formula that we're working with. Well, the base formula is the area of a square. What is the area of a square? It's s squared. Yes, it wasn't supplied on this sheet right here, but I think the majority of the people should know that the area of a square is side times side, right? Now, what do we know? Well, we got to know something, right? It's got to give us something else. It says each side of the square is increasing at a rate of 4 centimeters per second. So you see that phrase came up again, rate, increasing at a rate. So if it's increasing at a rate, that should tell you, oh, it's d something dt. Now it's saying the sides are increasing at a rate. So the side means it's going to be ds, right? The side is changing with respect to time. ds dt is 4 centimeters per second. If it was decreasing, if it said each side of a square is decreasing at a rate of something, then this would be negative right here, right? So you have to pay attention to what's going on all the time, whether it's increasing or decreasing, because the negatives will make a difference. What else do we know? Well, it's saying at what rate is the area of the square increasing when the area of the square is 9 square centimeters? So they're saying, okay, we see that phrase, at what rate is the area of the square increasing? That phrase, what rate, means, again, we have some kind of ddt, but this is associated with the area. So they want dA dt when the area of the square equals 9 square centimeters. So they're asking us, how fast is the square expanding at the exact instant when the area is 9 square centimeters, right? And we know that the sides are expanding at 4 centimeters per second. How do we figure that out? So dA dt is a question mark. Where are we going to get dA dt from? Remember, once you have your base equation, to get the dA dt or d whatever over dt, you have to take the ddt of both sides of your base equation. You will always do this purple step that I'm doing right here. That's always going to happen. You will take ddt of every side, the left side and the right side of all terms. So if we do that, again, implicit differentiation, chain rule, because these are all t's right here. The derivative of area with respect to time is just dA dt. Okay. What about this side, the right-hand side? This is going to involve implicit differentiation. Why? Because you have the power rule. So we have to say, oh, well, the derivative of s squared with respect to t is going to be 2s to the first. And then you have to derive s with respect to time. That's implicit differentiation. So you're going to have ds dt. So that is when you have successfully derived the area of a square with respect to time. So they're asking us, we want dA dt when area is equal to 9 square centimeters. So this is the question mark right here. But we have an issue, right? Because what do we need? We have a ds dt, but we don't have an s. They didn't tell us, oh, the side's like 10 or something. So we need to figure that out, right? We need s. Where are we going to get that from? Well, we can figure out s, right? Because part of it comes from here. They said they want dA dt when the area is equal to 9 square centimeters. So we can figure out exactly the length of each side at the instant that the area is 9 square centimeters. So how do we do that? We say, oh, if area is equal to s squared, we could say 9 is equal to s squared. I'm just plugging this in, right? Because area is 9. And then we solve for s. So you take, the square root of both sides. And you get s equals plus or minus 3, right? 3 centimeters. Now, would you go with the negative version? No, right? Because can you have like a negative area or negative side of anything? No. So you will just go with the positive version, okay? So S equals 3 for 3 centimeters. So let's plug all that stuff in, right? What are we plugging in, or where are we plugging it into? This equation right here. We have dA dt equals 2s, and then ds dt, okay? let's throw in what we know, right? Again, this is the question mark. We want dA dt. This is the question mark. So question mark equals 2. What's S in this case? We have 3 centimeters. ds dt, what is ds dt? They gave it to us in the problem. It's 4 centimeters per second. And then we multiply all this stuff out. So what are you left with? We have, oh, dA dt, or the area is going to be increasing at a rate of 2 times 3 is 6 times 4, 24 centimeters squared, or square centimeters per second, right? 2 times 3 times 4 is 24. Centimeter times centimeter is square centimeters, and you just bring the seconds along. So in this one, we had to do a little bit more work, right? We had to figure out what the side was specifically at the moment the area was 9 square centimeters. But how do we do that though? Again, we plug this 9 in to our area of a square, right? And we solve for S. And just don't forget, you're going to reject the negative value because we can't have negative lengths, right, of anything, or negative volumes, negative areas, stuff like that. So watch out for that right there. And again, if you have some kind of pi stuff that's in the formula, do not convert it to a decimal, all right? Now let's go to number 3. Three is saying a spherical balloon is inflated so that its volume is increasing at a rate of 2 cubic centimeters per minute. How fast is the radius of the balloon increasing when the radius is 3 centimeters? Okay, so we have this balloon, right? Spherical balloon. I'm going to try to draw a big old, here's a shadow, right? Shadow of the balloon, 3D balloon popping out of the page. But basically imagine the balloon, right? Hot air balloon, you're blowing it out, you're blowing it up or whatever. And it's just, imagine this is some 3D expansion or something like that, right? So how do we start this? Figure out the base formula. We're dealing with balloons are spheres, right? They're not circles. So we have, oh, volume of a sphere is 4/3 pi r cubed. What do we know? We know what? What do we know this time? Well, it says right here, a spherical balloon is inflated so that its volume is increasing at a rate of 2 cubic centimeters per minute. There's that phrase again, increasing at a rate. That means it's the derivative of something. So it says the volume is increasing at a rate of 2 cubic centimeters per minute. So if it's volume, we know that dV dt is equal to 2 cubic centimeters per minute. Okay. Now it's saying how fast is the balloon, or I'm sorry, how fast is the radius of the balloon increasing when the radius is 3? So they're asking, what is dr dt when r is equal to 3 centimeters? So let's look at that, right? How fast is the radius of the balloon increasing? When you see that phrase, how fast or how slow or something like that, that signifies the derivative. That signifies rate of change. Remember, rate of change is just derivative. So what is dr dt when the radius is equal to 3 centimeters? So the dr dt is the question mark. Once we identify what we know, right, and what we're trying to find, the next step is what? Take your derivative with respect to time, right? We're going to do ddt of both sides right here. All right, so the left side, the derivative of volume with respect to time is just dV dt. Now the right side, you have the power rule. Remember, 4/3 and pi are just constants, right? Pi is just a constant. It's an irrational number. It's not a variable. We need to really derive this r cubed with respect to time. How are you going to do that right there? What's the derivative of this with respect to t? Well, power rule, right? R cubed with respect to t, the derivative of that is 3r squared. But then we have to chain the r, which is dr dt, like that. Now let's simplify this, right? We can definitely simplify some pieces. So dv dt is equal to what? Well, look. Remember, this is all multiplication. We can knock out this 3 with that 3. And what are we basically left with? 4 pi r squared, and then dr dt. And now we just need to plug in what we know and what we don't know. What did we know? Well, remember, it said the balloon is inflated so that its volume is increasing at a rate of 2 cubic centimeters per minute. That was dv dt. So we have 2 cubic centimeters per minute is equal to 4 pi. And then do we have the r? We do, right? Because the rest of the problem was asking how fast is the radius of the balloon increasing when the radius is 3 centimeters. So this is 3 centimeters squared. And remember, dr dt was a question mark right here. That's what we were looking for. So now we need to solve this thing for dr dt, right? We basically have to isolate the blue chunk right here. Well, how do we do that? Before we get to that, though, we can multiply this out, right? Like this is 2 cubic centimeters per minute equals, this is 4 pi times 9, right? 9 square centimeters. What's 9 times 4 pi? That's 36 pi. And what are your units going to be? What's a centimeter squared? It's just centimeters times centimeters, which is square centimeters. And then we still have our dr dt. So we need to isolate dr dt. That means we have to move over this 36 pi to the other side. How do we do that? Well, it's connected to dr dt by multiplication. What's the opposite of multiplying? Dividing, right? So don't get all confused and go, I don't know how to solve this. Yes, you do. It's the same thing that you've been doing before. It's just we have, units with it, but it all operates the same way mathematically. So these get knocked out. So what's left over? We have dr dt equals, and I'm going to reduce the 2 over 36 to 1 over 18. We still have this centimeters cubed over minute up top, and we still have the pi and this centimeters squared on the bottom. Now, how do we reduce this right here? Because we still have the units, right? You got the centimeters cubed and the centimeters squared. Well, it's just like exponents, right? If you had x cubed up top and x squared on the bottom, how many x's would you have left over? And x the first up top, right? Same thing right here. So you're going to have 1 centimeter over 18 pi per minute. Just like that. Notice again, you're going to leave this pi right here, okay? Do not convert it into 3.14 whatever. Also, the pi stays in the denominator. Don't shove it up top. We had to divide that on both sides. It stays in the denominator, okay? All right, so we'll move to the fourth one. This will be the last one. I'm going to break up this section into 2 parts. Questions 5 through 8 will be the next lecture. Or is telling us, oh, the length of a rectangle is increasing at a rate of 5 centimeters per second, and its width at 3 centimeters per second. When the length is 11 centimeters and the width is 5 centimeters, how fast is the area of the rectangle increasing? So we have a rectangle, right? Got this. Do you need to draw the pictures? No, but it kind of helps out, right? We know we have area equals length times width. And this rectangle is growing, right? It's just expanding exactly like the square was previously. So it's, we can do this if we want. We know that, I'll just call this the length right here, the length of this thing. So it's saying the length of a rectangle is increasing at a rate of 5 centimeters per second. What does that tell us? That, dl dt, right? That's this component right here. So we know that, the length is increasing at a rate of 5 centimeters per second. And the width, this is like the length, right? The width. It really doesn't matter if you label this as the width or this is the length. It doesn't matter. Just the problem will work out the same exact way. So it's telling us the width is increasing at a rate of 3 centimeters per second. Then it's saying when the length is 11 centimeters and the width is 5 centimeters, how fast is the area of the rectangle increasing? So it's saying it's asking when the length equals 11 centimeters and the width equals 5 centimeters, how fast is the area of the rectangle increasing? So how fast is the area of the rectangle increasing? That should tell us, rate of change right there. So they want to know dA dt is equal to a question mark right there. That's what we're looking for. So we made our list of knowns, unknowns, right? Like what we're looking for. What's the next step? What do we do after we figured this stuff out? We derived our geometric shape formula, right? We did the ddt of both sides. So we have ddt of the area and then equals ddt of length times width. So left side, pretty straightforward, right? Derivative of area with respect to time is dA dt. Now the right side, though, we have two variables. We don't just have one. Remember, in all the other problems, we always had one variable. It was like just the radius or just the side of something. But if you have two variables, and we're multiplying them, how are we gonna have to derive them? With the product rule. So F and G. So let's do that. We have, remember, product rule is FG prime plus GF prime. So F times G prime, well, that's L. And then if we take the derivative of the width with respect to time, that's just dW dt. Plus, remember, that's F times G prime. You can make a little note of that. This is F times G prime plus G times F prime. So what's G? That is W. What is F prime? What's the derivative of the length with respect to time? That is dL dt. So again, why do we have to do the product rule right here versus the other problems that we were doing? It's because we had two different variables on the right-hand side. The other previous problems, we never had to do the product rule because we were only deriving one variable on the right-hand side. Right here, you have two unique different variables on the right-hand side. That is, and you were multiplying them. That's why you had to do the product rule. If you were dividing L over W, you'd have to do the quotient rule for them. So now let's plug in what we know and don't know, right? What is it that they were looking for? How fast is the area of the rectangle increasing? So this was the question mark, right? dA dt was the question mark. Let's just substitute in, they gave us these 4 values right here. The length of a rectangle is increasing at a rate of 5 centimeters. That was the dl dt, right? So we have 5 centimeters per second. And then the width was 3 centimeters per second. So that was the 3 centimeters per second for dw dt. And then it says when the length is 11 centimeters, 11 centimeters for the length. And the width is 5 centimeters. And again, we were looking for how fast is the area growing when these certain conditions are applied, or at this exact instant. So what do we get? We get dA dt equals, well, that's what happens right here. What's 11 times 3? It's 33. What's centimeter times centimeter? That's centimeters squared, or square centimeters per second, plus 25 centimeters squared per second. And then what's 33 plus 25? We can add these up because the units are alike, right? If these units were not alike, we cannot add them up. So 33 plus 25 is 58. And then centimeters squared per second. I'll put second, so that way you don't think it's a 5 accidentally. So again, it's been the same process over and over, right? What's really changing? It's the shape, right? You figure out what shape you're working with. Then the next step is figure out what they give you. They're always going to give you some kind of rate of change with some variable. You got to look for that phrase. Oh, a certain variable, the radius is increasing or decreasing, or the area is increasing or decreasing, a side's increasing or decreasing. When you see that increase or decrease, that should signify to you, oh, it's a rate of change, or it's a derivative of some specific variable. Write that down, right? Make a checklist like, we know this. And then after that, you want to know, what is it asking you to solve for? How, if it's saying, again, how fast something's growing or whatever at a certain instant, that's your d whatever over dt that you would be looking for. They're always going to give you enough information to solve these problems, okay? So that concludes part 1 of 3.9. I will upload questions 5 through 8 shortly, so stay tuned for that. That'll be the part 2.